Hello, today we are going to discuss about stream function and then Navier-Stokes equation in terms of stream function and Stokes law past a cylinder. So, to start with let us introduce what does it mean by stream function. So, introducing stream function. Okay. So, let us start with equation of continuity. So, you have divergence of u 0. So, if we represent u is in Cartesian u v w, so then divergence of u is denoted by this. Okay. So, once you have constant planes like x equal to constant or y equal to constant, z equal to constant, so then one you are suppressing one of the variations. So, in this case we are projecting 2D such that the partial derivatives with respect to z are 0. So, once you go for this restriction, what happens? So, this will be 0. So, then the equation of continuity reduces to dou u dou x plus dou u dou y equal to 0. So, then one can introduce this such that the equation of continuity satisfies identically. So, I would like to show you how this can be done. So, we are considering divergence of u 0. So, this implies dou u dou x plus dou v dou y is 0 in 2 dimensions. Okay. So, here you have a partial derivative with respect to x, here you have a partial derivative with respect to y. So, one can introduce a function psi such that since we have a partial derivative with x here with y, and since we have a derivative with respect to y, we introduce partial derivative with respect to x, then a psi, and since we need an identity, so you can take a negative sign here. So, psi equals to psi is function of x y, and this is called stream function. Okay. So, alternatively one can also define this negative sign so this definition also will give a identity. Okay. So, only thing the corresponding velocity direction is controlled by the sign. So, if it is left to right, the otherwise right to left. Okay. Otherwise, both the definitions are valid. So, what is the physical significance of such a stream function? Okay. So, as you know, suppose you have a uniform flow. So, then what we assume constant with a constant magnitude. So, then if you take along x axis, maybe you have lines like this. So, what are they? These are called stream lines, right. So, stream function can be used to represent the stream lines. Okay. So, one can use this and then try to plot the stream lines. How I will explain with a couple of examples. Okay. But so, let us say if you switch over to plane polar coordinates. So, then this is the equation of continuity. So, 2D plane polar coordinates, we have this equation of continuity, that is divergence of u 0. So, then here also we can do a similar trick. If you see here we have the r derivatives and here we have theta derivatives of the corresponding velocity components. The notation that we are using is velocity vector is represented by the components u r and u theta, namely radial velocity component and tangential velocity component. Okay. So, we are please do not misunderstand these subscripts with partial derivatives. So, these are to indicate the components. Okay. So, now we can consider this equation of continuity and introduce, as I indicated, you have an r derivative here and theta derivative here. So, for psi we are introducing a theta derivative, and for u theta we are introducing r derivatives in terms of psi, and you can see if you substitute u r and u theta as defined by this, we get an identity. So, that means this is the relation for plane polar coordinates. Okay. So, similar thing one can try for other coordinates, but there is a big restriction. So, what is the restriction? So, the restriction is, so far we discussed divergence of u equals to 0. This implies dou u dou x plus dou v dou y plus dou w dou z equals to 0. But restricting to 2D, we have, and then we could introduce, since we have x derivative, we introduced a y derivative if we have a y with a negative x derivative, and we have introduced u equals to dou psi by dou y, v is. Okay. Now, the question is, can we introduce for a general 3-dimensional equation of continuity such a function? So, unfortunately, we can't. Okay. So, you can see whatever may be the combinations, you will not be able to capture this in terms of one single scalar function. Okay. So, similarly, when it is a 2D plane polar coordinates, so we have only two velocity components, and then we have introduced the corresponding stream function in polar coordinates. Now, the natural question is, can we do it in higher dimensions? So, let us consider cylindrical polar coordinates. Okay. So, here we are representing the velocity components as u r, u theta, u z, and the equation of continuity is given by this. So, can we introduce stream function? Okay. We have three components. Can we represent these three components in terms of a single scalar? So, the answer is no. So, then in which simplified situation we can introduce? For plane polar coordinates, if you introduce axis symmetry, we discussed this before. So, that means variations with respect to theta are not there, then reduced equation of continuity is given by this, which is in terms of radial and z components. Okay. So, now again if you observe, we have an r derivative and we have z derivative. So, therefore, one can introduce a stream function as follows. Okay. So, one can introduce stream function as follows, u r and u z. So, this is the corresponding stream function in cylindrical polar coordinates. Okay. So, now finally, we have spherical polar coordinates. So, again if you see, so this is u phi, this should be u phi. So, u r, u theta and u phi. So, this is the equation of continuity. Then axis symmetry in terms of spherical polar coordinates is all the flow quantities are independent of the azimuthal angle phi. So, then reduced equation of continuity is this, and one can define. So, this whole quantity with the theta derivative and this whole quantity with r derivative we are introducing. That is what we are doing. You see, this is with theta derivative and this quantity with r derivative. So, once you introduce this, that will define u r, and once you introduce this, that will define u theta. So, this is the corresponding stream function. Okay. So, in summary, what we have in Cartesian, the definition of the stream function is this. In plane polar, this is the definition, and in cylindrical, this is the definition, and in spherical, this is the definition. Okay. So, natural question is, what is the advantage of introducing stream function? So, what we are saying is, if you are in arbitrary 3 dimensions, definitely as of now we have to use only the primitive variables, that is velocity components and pressure. But if you are in 2D, maybe one can introduce auxiliary variable, that is stream function. Okay. So, what we have seen so far is one can introduce stream function in either 2D or 3D axisymmetric. Okay. So, the vector equations can be reduced in terms of the scalar equation, which is by virtue of defining stream function. Stream function being scalar, so all the vector equations can be converted into a corresponding scalar equation. So, we will see before we solve any physical problem using this approach. Okay. So, but before that, so once you have a corresponding vector quantities, using this relation we should be able to integrate and obtain the corresponding stream function. So, how do we do it? So, let us take an example. So, this is example to convert stream function. So, let us say the velocity is so this is unit vector and u is constant, which means this is supposed to be uniform velocity along x direction. Now, using a stream function, we have u is dou psi by dou y and v is minus dou psi by dou x, but from this what we have is u component is u and v component is 0, okay, because there is no z component, therefore, v is 0. So, from this what we get is u is function of y alone, right. So, then from here one can get psi is u y plus a constant and we have d psi dx is 0. So, if we use this implies c is 0. So, therefore, what we have is u times y. So, corresponding to the uniform velocity u I, we have the stream function u y. Okay. So, once you have the stream function, we can represent the streamlines. Okay. We can represent the streamlines. Suppose using contours. So, what are the streamlines? Psi of x y equals to constant. So, they represent streamlines. So, these are the. So, in this case what we have is u y equals to some u tilde or y equals to some constant. So, you can see. So, including y equals to 0. So, these are the streamlines. Okay. So, once we have vector form velocity, we could get the corresponding scalar and then one can get the corresponding streamlines. Okay. So, this is very useful tool. So, but with a restriction. What is the restriction? We can introduce a stream function in 2 dimensions or 3D axisymmetric. Okay. So, now let us see how Navier-Stokes equations can be simplified. So, there will be a bit of algebra, but some I would show and then some you can work it out. Okay. So, another important quantity is curl of u in Cartesian. If you take, so this one can check very easily, and since we have 3 non-zero components, assuming u v w do not give, so generic sense, therefore, non-zero we are assuming. So, omega 1, omega 2, omega 3. So, these are the components, each of them we are calling, and this is called vorticity. So, vorticity basically indicates the rotation. Okay. So, it indicates if vorticity is non-zero means you have a rotation flow happening. Okay. So, that is a vorticity, and similarly if you have only 2 dimensions, then you will see for any general u v w. So, you have only one component. So, that is given by this. So, we call it only omega 3. Okay. So, we have 2 scalars one is stream function and curl u can be represented in 2D in another scalar, whereas in 3D omega is also a vector. Okay. So, now there is a relation in 2D that is called, if you simplify, see V is dou psi by dou x, u is minus dou psi by dou y. So, we get Laplacian. So, this is, and if you see 2D, this is exactly the third component of the vorticity, okay, third component of the vorticity, which means del square psi is equals to the third component of vorticity. Okay. So, we are defining stream function vorticity relation. So, that is del square psi equals to omega, assuming this is omega 3 and the psi is stream function. Okay. So, this is very useful tool to convert the corresponding vector equations in terms of stream function vorticity formulation. So, which we are going to do now. So, that is the next section, Navier-Stokes equation in terms of stream function. So, let us consider Navier-Stokes equation of a viscous incompressible flow, and we have ignored the external forces. Okay. Now, we restrict the dimension to 2D, because in 2D we have stream function and vorticity. Okay. So, what is our aim? Our aim is to get rid of primitive variables and convert these equations to equivalent equations in terms of stream function vorticity. Okay. So, these are the component form. Then one can eliminate, you see this is a pressure is having partial derivative with respect to x and here y. So, our aim is to eliminate pressure. So, one has to differentiate this with respect to y and differentiate this with respect to x and subtract. So, we do that. So, once we do, you see this with respect to y minus the second component with respect to x. So, this is what is done, this whole thing with respect to y minus this thing with respect to x. Okay, we are subtracting, right. So, that is what is done. So, it is a simple algebra. Now, let us group some terms so that we can quickly identify. So, what we are grouping, so this time derivative we have taken out. So, that will be dou u by dou y and here dou u by dou x, then y derivative of the entire term, then similarly x derivative of this entire term, then so these two are given, then the right hand side you can see this is a Laplacian and this is Laplacian. So, they are as it is. So, now we have our stream function definition. So, we introduce the corresponding definition in the above equation. All that we have done is simply substitute corresponding u and v as it is. We do not do much. You can see del square u becomes this, del square v becomes this. So, this is not much we have done. Okay. Now, you see if you expand little bit, so some terms get cancelled. Okay. So, in this produces two terms, this is a mixed derivative and dou by dou y operating on this. Okay. So, if you do the complete expansion, some terms get cancelled. You see this term and this term are similar with a negative sign and this term. Okay. So, some cancellation occurs and we get. So, this is a simple algebra. So, it is not very difficult, one can follow, almost I have given almost every step. Okay. So, then the simplified remains this. You can see how this is by Laplacian. Okay. So, you have a Laplacian and it is Cartesian coordinate. So, they commute. So, Laplacian comes out and this goes in and we have a second derivative with a negative sign of y square, and similarly here we have a second derivative of x with respect to x and minus sign. So, therefore, we get minus nu del 4 psi. Okay. So, this is what we have. Now, this can be put it in a compact form further, you see. So, this term is brought to the left hand side and the remaining terms they are put in a compact form. Okay. This there is a symmetry psi with x and Laplacian of psi with y. So, psi with y, Laplacian with x. So, this is exactly nothing but the definition of the Jacobian. Hence, we got a simplified Navier-Stokes equation. Okay. So, now the equation as it stands, what we have achieved is really we have converted the vector Navier-Stokes equation in 2D via component form to a one single scalar equation. Of course, it is nonlinear, retaining the nonlinear structure of the Navier-Stokes equation. Okay. All that we have achieved is we have converted into a scalar equation. So, one has to solve the corresponding nonlinear scalar equation. Okay. So, this will be further simplified depending on steady case or if it is a Stokes flow. So, correspondingly, if it is a steady Stokes flow, what we have seen, if it is steady, there will not be any time dependency. So, therefore, this has to go, and then if it is a Stokes flow, inertial term is not there. If you see, this is due to the viscous term, that is how the kinematic viscosity is multiplied, and this is due to the inertial term, that is how the nonlinearity is sitting in this. So, now if it is a steady Stokes equation, then we are neglecting time dependency and we are throwing away the nonlinear terms, inertial terms. So, then we get simply stream function satisfies biharmonic equation. Okay. So, that is one. So, now similar approach can be done in polar coordinates. Well, the corresponding algebra that we have done for Cartesian is slightly manageable. We can straight away substitute and then do this kind of manipulations. A similar thing one has to do in plane polar coordinates. So, that involves little bit of calculations, but it can be done. Okay. So, even if we do that, we are going to get the same. So, it is as long as you are in 2D. So, the final equation is going to be the same when it comes to Stokes flow, because you do not see the nonlinear terms, but once you have nonlinear terms, then the Jacobian will be in Cartesian, it will be in terms of Cartesian, and in polar coordinates it will be in terms of polar coordinates, as you can see here. Okay. So, even in this case steady limiting both are same. Okay. So, this is about Navier-Stokes in terms of stream function. Okay. Now, our job is, if somebody wants to solve Stokes flow past some object using say a stream function, then we need to find a solution of this, right. It appears complicated, but we can handle. Why we can handle? This is a linear operator. So, that is the biggest advantage that we have. Okay. So, let us see. Now, next section is we would like to use this scalar function and then solve some practical problem. Okay. So, the first problem that we are discussing is Stokes flow past a circular cylinder. So, when you say a circular cylinder, we are not talking about flow past a cylinder like this. Okay. So, we are taking about vertical, so the flow across the cylinder. So, that any time we see a 2D projection from above. So, this is a 2D problem. So, let us consider Stokes equation. Okay. So, this is conservation of mass and then momentum balance. You have seen unsteady, okay. Then steady case, we have viscous terms and pressure terms, and this is equation of continuity. Now, let us introduce the problem. So, as I indicated already, we are considering uniform velocity at far field, okay, and we are placing a cylinder and we are discussing flow past this cylinder. So, as I already indicated, the problem is 2 dimensions. So, we are seeing from top. So, we are seeing a circle. So, it is essentially flow past a circle, okay, and the corresponding velocity can be decomposed into radial and tangential, and we assume that. So, there is no flow across the cylinder. So, therefore, no slip, right. So, we introduce r and theta coordinates. So, now what is the tool? The tool is the stream function. So, this is the equation of continuity in plane polar coordinates. Then we have introduced the stream function. Then the corresponding boundary conditions that we have are the no slip condition, that is the normal velocity 0 and the tangential velocity 0. And the far field we have uniform velocity. So, this requires a little explanation. So, we are considering a cylinder given by r equals to a, and here we are considering a far field velocity, but we are not solving the problem in terms of velocity. We would like to solve the problem in terms of stream function. So, corresponding to this we have to get the stream function. Okay. So, how do we do this? This you can decompose u cos theta minus u sin theta. So, how we are getting? I has been decomposed in terms of r and theta. Okay. So, correspondingly we get this. Now, from this we have the stream function velocity, okay, relation. So, we use so this is u r comma u theta. Okay. So, from here u r is u cos theta. So, this decomposition we do, and there should be an r there. Okay. So, this is equals to okay. Okay. So,